Okay, so we ended with looking at interactions on graphs. So let me talk about this idea some more. So these were taken from the Andy Field book, so let's look at those real quick. But the main way you can see an interaction in a graph is that they cross. I mean, that may not be significant, but that's a good start to seeing it. Anytime the lines are parallel like this, there's no interaction. Now there is still an effect of our different variables because this point here and then this point here are their different heights, but there's no interaction. You can also see that looking at graphs because these have the same pattern of effects versus this pattern of effects. So I find it's a little harder to see in bar charts. Line graphs are a little easier, but you can tell by looking at the pattern of the bars versus the lines for a line graph. So let me draw you some examples. So we have gender and sport here, and so I'm going to put sport on the bottom here, and then do satisfaction out here on the Y, and then we're going to draw lines for gender. So if I want only a gender effect and no sport, so across sport here I'm going to make it flat. So there's 3 lines here, and then I'm going to make this male and this female. Okay, this would be an effect of only sport. Only gender, because the sport lines are straight, but the gender lines are separated. Okay. In bar graph form, what this would look like is, and I didn't really leave myself enough room. Let me kind of hijack my graph here and make it a little smaller. Go away. Shrink. Okay, so this would be line graph form. Okay. Bar graph form, what we'd see where you get that same picture, straight line. Okay, so that would be only gender, where this is male and this is female. If I instead want to get a sport interaction, so still sport down here, but no gender, so satisfaction on the Y. Let's see, so sport, we would need to make them different heights. This is no interaction. So this is the line graph. Okay. But men and women are going to have the same bars. Okay, so men and women together, and then men first and women second in this graph. So there's no effect of gender here, so this is sport only, because the gender lines are the same. Okay, so they're on top of each other. If they're on top of each other, there's no effect. The next thing I'm going to show you is what's called a perfect interaction. So this would be only the interaction, and no gender and no sport. Okay. These are sort of rare, I feel like. Normally you get at least one interaction and one main effect, if anything. Or only main effects, but you can see these perfect interactions. Okay, perfect interactions in line form are perfect X's. Where this is men and this is women, or females. And so what you'd see is the set of bars for guys makes a different pattern, the exact opposite pattern than the set of bars for girls. So you get this perfect cross interaction effect. And so I kind of drew this poorly here, maybe more like equal there. There we go. That would work better. And that would be a perfect interaction, only the interaction. All effects can look lots of different ways, so I will try my best here to give you just one. Okay. So that might be where we have equal groups for one sport, very unequal groups for another sport, but then the opposite pattern for the last sport. So it might go like this for one group, and this is sort of what we get, and then like this for the other group. Okay, so this would be men and this would be female. And so you get these different patterns depending on which group we're looking at. Okay? And so that would be all of the effects. Okay? This actually might average out where there's no effect of sport. But this would be one example of where you couldn't necessarily tell just by looking at a graph. So I've got an interaction and something else is going on. No effects is very easy to see. It's usually a very boring graph where all the lines are exactly the same because there's just no effect of anything. So this would be men and women have the exact same line. Right, so be sure you study those kinds of graphs and be able to label which types of effects there are. So a general rule is flat lines are no effects, parallel lines mean no interaction, and any kind of unseparated lines where they're the same line is no effect as well. So I have an interaction in my study, now what? We talked about before, your options are post hoc, right? We didn't do contrast, but that was one. You could do trend analysis, or you could do no correction, which is a bad idea just in general. And we mostly focused on post hocs and trend analysis. Since I have interactions, trend analysis isn't necessarily the best idea, unless you want to do different trends for different groups, and then you're doing moderation, so you should do a different type of analysis. But post hocs can really be on main effects or interactions. And when they're on interactions, often they're called simple effects analysis. So that's just a fancy term for specifically an interaction on a post hoc test. So we still have to be concerned with this type 1 error rate. And we still have to do something about it. The other issue is back to family-wise or experiment-wise. And so let's say I have 3 effects. I have gender, sport, and the interaction. We talked in the previous video how the interaction is either 3 tests or 6. Gender is no test, and we'll get to why in a second. Sport, since I have 3 conditions, 3 levels is 3 tests. 1 to 2, 2 to 3, 1 to 3. And so I could control these family-wise once within each ANOVA. So I would control for the 3 here, and that's it, and then the 3 or 6 here, and that's it. Or I can control experiment-wise across the whole shebang and control somewhere between 6, I can't add. 6 to 9, so add them all up. Okay. And that would just depend on how you analyzed your interaction. So family-wise is more popular because it's more power to detect effects that are there, especially because the ANOVAs have separated out the variance due to the interaction and main effects separately. So I'm not testing the same cookies twice. One suggestion is that if an interaction occurs, you will not analyze the main effects. This is old, scratch this out. You don't get these automatically in R, you do in SPSS, sorry. So when the interaction is significant, people often suggest to just totally ignore the main effects because the conditions matter. And if the conditions are what's important, why am I analyzing one variable at a time? And so if you get the interaction, usually people ignore the main effects. But sometimes people say, well, I still want to know what happens when that variable occurs in isolation. I'm on the camp of just run the interaction because that's the important part anyway, but you will see it both ways. Now, the super important thing to realize is that you do not run post hoc tests in any form on a main effect that only has 2 levels. Because remember that, ANOVA equals t-test squared with only 2 levels. And the whole point of post hocs, usually, if you're going to do the type of post hocs we're talking about, is that they're pairwise. So 2 by 2. If I only have 2 levels, I'm already doing it pairwise. Why would I do it twice? So essentially, you would just look at the means and compare them to each other and talk about if they're significant or not. So don't run the test twice. So gender only has 2 levels, so we would just look at the means. We've already talked about how gender is not significant. Men rated sports overall the same as women. Okay, and these were not significant, so we'd have our F test out here. And we mentioned it earlier when we were talking about writing them up. If I wanted to analyze sport, I could use the post hoc, just like the one-way analysis that we talked about in the chapter 10 video. And I will show you how to do that now in R. Okay. So we're going to use that agriculture library that we did before. Sorry, that was probably pretty loud. Keep. Continue. All right, back to Studio here. So I have the code here on how to plot the graphs, which I'm just going to kind of skip for right now. You can run that one on your own. So I'm going to install this agriculture library real quick. So you can tell I'm not on my Mac because my Mac is very clicky when I type on it, but this keyboard is not. So what I'm going to do is use the Tukey test. So remember that post hoc tests are t-tests normally, and this is going to be independent t. And now it's independent t because we're using between subjects, and independent t matches between subjects because they're in different conditions, or levels in this case. And then so I can use the hsd.test to run Tukey, so that'll correct for 3 tests: none to football, none to volleyball, football to volleyball. So I saved, it's the output that's been saved from my ANOVA. Sport, which gives me only the IV sport, so I could do gender. If you had 2 main effects with more than 3 levels, I could test each one separately. Group equals false, console equals true. And so, oops, load the library. Do that once a day. There we go. And then it gives me my output, which I put conveniently over here for you guys. This is a little bigger, easier to read. And so it gives you the means and standard deviations and n. Remember, this R here is n. And I could plug those into Mote and get the different effect sizes, or you can calculate effect sizes by hand. And it's clear that football and none are different. None is rated higher because that mean is higher here. Football and volleyball are different. Volleyball is higher. None and volleyball are not different. And I got that by looking at the p-values. Now I want to run my simple effects analysis. So I'm going to analyze across or down. And I want to analyze with the smaller number of levels. So what does that mean? So if I've got male and female, it is smaller to go this way. But to do that, so this is non-football, volleyball, I'm going to have to split these into different groups. So I've got to split them out where none is its own data set, and I could do male versus female. Where football is its own data set, and I could do male versus female. And where volleyball, again, their own data separated out. Okay. So stick with your hypothesis first, or the smaller number of levels. But that means that we have to split on the larger number of levels and analyze on the smaller number of levels. So this I'm talking about analyze. In a minute I'm going to talk about splitting on the larger number of levels. We're doing a between subjects ANOVA. Therefore, the follow-up test is independent T. The correction, we could do Tukey, could do Chaffee, Bonferroni, or S&K, like we talked about last week. But we can't use that library directly. So we're going to coerce it into doing post hocs for us by splitting up the data set on the larger number of levels. So this is talk about split, not analyze. This is splitting up so we can analyze. And I'm going to subset my data out by using the subset function. And then what I'm going to do is I'm going to run an ANOVA on each one of these subgroups, save their output, and then run the post hocs using the agriculture library. Okay. If I just looked at this, this would have no corrections. I don't want to do that. I want to use this as a step to get here. Okay. Remember that IV name should not be the split. So you basically are creating two variables. Your analyze, so we're going to analyze based on gender to get a smaller number of effects, but we're going to split based on sport. Okay. And so analyze, so this is going to be my AOV, and this is going to be my subset. Okay, so keep those straight. You cannot split and then analyze. It will be very unhappy with you. Okay. So those are the answers here. Let us now look at how to do it. Okay. So we're going to split the data set on the larger number of variables. So I'm going to create a none data set by subsetting the data set where sport equals none. Remember, this has to be right here, double equals. This is a logical question. Is sport none? Yes or no? And it will pull all the yeses for you. So it's got to be double equals. If you do one equal, you will not get what you're expecting. And they do have to be spelled exactly like they're spelled in the data set. So watch, when I run this, I'm going to get a new data set up here that says none, and it should have less people in it than the original data set because we are separating them out at this moment. And then football and volleyball. Okay, so these 3 16s add up to my 48, so I've just created 3 little mini data sets with only one sport in them. Okay, but because I've split them up, I don't want to include sport anymore. So now I've got satisfaction is predicted by gender, and I've separated out the data sets. So those 3 data sets that I created here, I now have them down here. Okay. So I've got my output temporarily, because I'm going to use it to run down here. Oops, I don't know what I just did. Uh-oh, no. Not markdown. Script, there we go. Confused it for a second. And so I'm going to use my HSD from the output I've created on lines 112 through 114 to get my 3 Tukey tests. And that will give me corrections. And I included those here. So let's interpret this output. So by looking here at my p-value, I can tell that the difference between men and women in the none condition only is not significant. So if men and women are not going to sports, they have an equal rating of their satisfaction with sports. For football, there is a significant difference. Women are much more satisfied with football than men. In volleyball, there is not a significant difference. Men and women have the same rating of volleyball. Okay. And if we go back a bunch of slides here, see if I can get there. Yada, 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 yada. And we look at our exact graph that we were interested in. Here we go. You see that. So none, there's no difference here, there's no difference here, and there's a difference here. So it should, this is why I always make graphs, it should match the graph that you made. So you might not, they may not be significant, but it should at least look kind of like what the graph is. So there's no difference for none, there is a difference for football, no difference for volleyball. Now, I would want to calculate Cohens D or Hedges G for each of these post-hoc tests. So I would use these numbers here at the top to calculate, remembering that this is in, and include those in the write-up. So when you're doing a write-up, what you want to do is you need to make sure you include the omnibus test, that's F for each IV. So you're going to have 3 Fs. If you have more than 2 variables, you'll have even more Fs, and then any post-hoc tests. So these will be P and D, since we're using this library to calculate. It doesn't give me T, so I'm going to use P and D. Okay, so F should have P and some form of effect size. I like partial eta. Some people, you could structure it like this, by hypothesis. So gender, F test, post hoc, F test, post hoc, interaction, post hoc. And that would make more sense if you were going to run post hocs on every last little thing. If you don't want to run the post hocs because of the interaction, do all of your ANOVAs, and then all of your post hocs, and then a figure. Either way is perfectly acceptable. You'll see people write in both styles. I tend to do big tests than little tests, so I'm more of this style. But you could also do these this way, especially if you have very specific hypotheses that require you to run every single post hoc option. And so that is how you do two-way between subjects ANOVAs, including post hoc tests for interactions.